So let's start like this. We have seen this. But now we have groups, and we want to derive a new regularizer. And we've done it for an hour and a half, so maybe some of you can tell me how to do it. This guy doesn't know that there are groups. We have to tell this regularizer that there are groups. How do you do it? Anybody was here 2 days ago? Yeah.
So like assemble a vector of norms of each group and then do the L1. Okay.
Right. So we give ourselves a bit of notation. We want to talk about the coefficient that correspond to the entries of this vector W. So this is the W vector. And we call W1 this guy and W2 this guy. So it's like the entries of the vector that corresponds to the group 1, group 2, and so on. And we said, OK, this is what we're going to do. We're going to first consider a vector of norms. And this is just the L2 norm. OK? It's just the usual L2 norm without the square, and it is very important. So this is, for example, W1 square J. J is from 1 to what? The length of this vector, which is what? The size of the group that we were doing. So if you let me call calligraphic G1, the set of indices in that guy, the cardinality of this set is how big is that guy. This is the one bit of this notation which is kind of annoying, keeping track of all these sizes. And that's why I'm omitting it in the norms, otherwise it gets super overloaded with notation. Okay? And then what do you do? Okay, now that you have this vector, you're going to consider, so this is the L2 part. And then we do L1 part, which is considering sum of WJ. WG. G is the total number of groups, okay? And now this is what we want to use. So this is the L1 part. And we call this thing the L2, the L2 L1 norm, okay? Or L1 L2 norm. No, I'm getting confused. One of those. All right? Okay, so intuitively, this is the L1 norm on this block of norms. So if L1 does what L1 does, which is setting to 0 its coefficients, now the coefficients are not one number, but or they're like a number that is now somewhat agglomerating all the coefficients on all the elements of the group. So if this is 0, it means that all the W's are 0, because I'm summing up positive terms. So the only way I can make a 0 is by setting all the coefficients to 0. So if this L1 does what it's supposed to do, which is setting one of these terms to 0, it means that the whole group of all the coefficients in group is going to be set to 0. Does this make sense? This is the basic idea. Okay? Yep. Yes. This 2 is actually under 1. Yeah, and actually we discussed quite a bit why the square root is so important. And we said it's important, and it's important is where it is. So if I take away the square root, I just have L2 norm, because it doesn't matter that I split it in a bunch of different sums. It's just a bunch of squares, and it's an L2 norm, and it won't have any sparsity properties. If I put the square root instead of this norm, I get L1, and again, it will be sparse, but then I don't have any group. So in some sense, this square root is trapping all the coefficients that correspond to a particular group, and is what allows us to actually be selective to groups. Okay? What we did is also considering the way to solve the problem, which was essentially, where do I have it? It was essentially a Brock thresholding procedure. Let's see if I can remember it. So the idea is that, again, you do the usual prox. So it's WT plus 1 equal prox gamma lambda of WT minus gamma x hat transpose x at WT minus y hat, where let me call this RWGL is the so-called group lasso penalty. And so that now I can tell you that this is the GL. So it's a proximal method, unsurprising. This is convex and smooth. This is convex non-smooth. The good news is, again, that we can give this guy as a nice expression. It is actually given by the concatenation of a series of nonlinear operation over the blocks. So this prox operator acts in blocks, okay? So it acts on all the different groups. I use blocks and groups kind of as a synonym here. So it works on the first group separately from the other groups, okay? And what it does on the first group looks very much like soft thresholding with the difference. So if you remember, in the case of L1, here we had our soft L1 thing with the, and then we're doing, so W1. And then I can describe what happens to this at every component. And what happened is basically that I'm going to check what? If I do the component j of this, I'm actually going to check the norm of the block. Okay, I'm just doing group 1 just for the sake of simplicity. You can put group G. Doesn't matter. I'm going to check if this is smaller than alpha. And if it is smaller than alpha, what am I going to do? I'm going to set all the coefficients j to 0. Okay? And if it is bigger than alpha, what do? Well, you would like to do something like this, which is just keep the coefficient. You don't. As we did before, you're going to just change this slightly. The way you do it is by adding alpha W1j divided by the norm. Okay? It's kind of, if you think a bit about it, it's kind of what you would hope for. Okay? Rather than looking at individual coefficients, you now look at the norm of the block, and then you check if it's big enough. You let it be, shrinking it a little, or if it's small, you just set everything equal to 0. Okay? And if you remember, in the case of L1, we take 2 routes to convince ourselves that we were doing sparsity. One was the geometric one with the L1, L2 balls and hyperplanes and blah, blah. The other one was just simply taking a look at the soft thresholding algorithm. Here, we're just going to do the latter. Okay? If you look at this, it's clear that this method, when you solve it through this proximal forward-backward approach, is going to give you sparse solution in blocks because of the specific form of the prox operator. That makes sense? So as you run the algorithm, you do gradient descent, and then all you do is that you do this block thresholding operation. And again, you can appreciate the fact that the prox operator has a particularly easy expression. Okay, and so this is what makes this nice. Do you remember how to choose gamma? Anybody, actually. Sometimes if you look at somebody, you raise your hopes.
Biggest value of the Hessian
Of what?
of the original functions, like the original.
Right. So I just repeat what he said there. As you choose gamma as if this part was not there, and you wanted to use gradient descent. Okay. Which is doing what? What he said, which is take the Hessian of this, or anyway, take a bound on the norm of the gradient of this and use it. Okay, so that's kind of nice. These algorithms are kind of nice because they decouple the contribution. Everything is hidden in the computation of this. Sometimes it's trivial to derive it, sometimes it's not, but you see that the end algorithm is very simple. Okay. One can show that compared to subgradient, this algorithm has much faster convergence rates. Okay, if you go in, and I think in the appendix I scribbled the convergence rates of the different methods, perhaps. You should check that this method it really behaves. Even the proof of the convergence of this is basically a lifting of the idea for gradient descent. It looks very similar, so it's kind of cute. If you know gradient descent and you pass to this, it's kind of nice to look at the proofs and the idea because they really generalize this idea nicely. Okay, so what were we left to do? So any question about everything so far? So what we wanted to do was start to generalize this, questioning the very first assumption we made. We are happy to move away from individual variables. We are not so happy to make this restriction of having non-overlapping groups. Okay, so what we want to know is, and what if these guys are overlapping? So there is a whole region where I have variables that appears in more than one group. Okay, and you can really think of a lot of different situations where this might be the case, and we're going to comment it perhaps a bit in the end, but you can also think of this as a first step to pretty complicated situation, because the moment the groups can overlap, you can actually have groups that are contained one into the other, and then you can have groups that describe some complicated structures like graphs, trees, and so on and so forth. Okay, so we're just going to consider this, but you can see this as a first step to a substantial generalization of the whole story. All right, so we basically have to ask ourselves, what do we want to do with the intersection of these guys? Okay? When you have overlapping groups, what do you want to do with the stuff that is in the middle? And we're going to get there by first asking a question, which is, suppose that I use whatever is on the board already. Okay? I ignore the fact that you just told me, or I just told you, that the groups are overlapping, and I use this anyway. And then I go and look at the solution I have. What am I going to get? Suppose that you have this simple case when you have two groups, okay, and only one of them is important. Then I run this algorithm, and what am I going to get? A solution that has which component different from 0? Let's say that the important group is the first, and the not so important group is the second one, okay? I run whatever, I use this penalty, and I run this. What am I going to get? I get a vector, and which entries are non-zero?
Only the entries of group 2, all the entries of group 2 are at 0. You get all the entries of group 1 minus the one that are.
Right. So you basically, what he just said is, because this algorithm goes in, look at some entries, and set them equal to 0, and it just kills them, okay? If, when you look at group 1, you would like to let them live, but then group 2 comes out and say, no, I'm going to set everything to 0. So everything from here on is 0. So what I get is not a group of variable, but is a part of it. What exactly is the complement, okay, of a group? So you take this group, and then you take its complement. Notice that if I had more groups, the story would be the same. I'm basically discarding group, and so what I'm left with is the complement of the group, which is what I haven't discarded. Okay? It's pretty clear, right? I'm killing some stuff, I'm left with whatever is left. All right. Yep.
So from applicative point of view, so why would you assign one?
Which point of view?
From applicative point of view, I guess. So why would you assign one variable to be in multiple groups if this is the behavior?
Why would ever be the case? You can think of many situations, and again, one thing you can think of is, again, the analogy I made. One example I made is, suppose that you have a situation where you have variables that are biological measurements, okay, and you have that the biological measurements are grouped in measurements that correspond to biological processes, okay. You know, one example there was is like gene expressions. So you have certain gene expression, then other gene expressions, and like, again, you take 100 measurements, and then you have that some part of them is biological process 1, and some part of them is biological process 2. It's very reasonable that a gene is more than one biological process, right? Then it would be in two groups. And this is just one possible example, okay? If you go in the direction of hierarchies, you might have a situation where you have many variables, okay? But they have a spatial connotation. So for example, you say, you know, I have variables that correspond to spatial position, and having just all possible position, I'm going to divide the space in regions, okay? And I'm going to divide, say, in 16, and then in 4, and then in 2, and then I keep on going. And then I have that variables now are divided spatially in groups, and these groups overlap, okay? Because clearly if I divide in 4 or 16, they're going to have variables that belong to more than two groups, okay? And this stuff, for example, if you try to use something like this to learn some kind of segmentation of an image, okay? So these are just two examples, but you can invent as many as you want. That makes sense? All right, so you are in this situation, and we just learned that if you just keep on going with what we have, we're going to break groups and going to select what the complement of a group. So the question we want to ask is, what if actually a group matter, and I want to select groups, not discard groups? How can you handle it? So the thing is slightly complicated, because even just from a pure notational point of view, we have to have attention on what we're doing, because you see, the nice thing about this case where you don't have overlap is that if you have a vector, if you talk about a vector or its parts, the elements is a one-to-one correspondence. I give you two pieces, there is only one way to compose a vector. I give you a vector, there is only one way to break it into pieces. You agree? The way around. If I give you a vector, you can still decide that there is, you give a canonical meaning to this notation W1, WG, which is just take the first entries of this and take the first entries of this. Okay, so you have this vector, this long vector here. Group 1, group 2, this is called W, and we agree that W1, W2 is the same meaning as before. These entries and then, these entries. But suppose that I give you a vector, and I wanna, I wanna find how many ways I have to build this vector out of vectors of this length and this length. Okay, take a vector B1 and a vector B2. B1 is a size what? R cardinality of G1, and B2 is R cardinality of G2. The point I'm trying to make is that you can, if you want to build this guy, you can choose different sets of vectors, right? There is not a unique way to disintegrate a vector W. This is one, okay, and we can agree that say that's the one canonical version, but I have many possible ways to realize a vector W as the superposition of two vectors B1 and B2. Can you give me two examples? Let's just make a simple case. I have, this is my vector, 1, 2, 3, and this is group 1, and this is group 2, okay? Just to make it super simple. Well, I could take 1, 2, 0, 3, okay? See? Okay? Will be basically fine, and this guy doesn't really matter, okay? Or I can take 1, 0, 2, 3, and I can keep on going. I can do a lot of different things. Let's make this a little more precise, okay? Let's give ourselves a notation that allows us to talk about the long vectors, okay? So I want to use the notation with a bar on top of this vector. So I'm going to use the notation B1 to describe a vector that has the entries correspond. This vector is going to be in RP. And it's going to have, in the entries that correspond to this guy, this group is going to coincide to B1. Everywhere else is going to be 0. Does it make sense? So suppose that I give you this vector. This is B1. Okay, how much is B1 bar? 1, 2, 0. So it coincides to B1 in the entries that are in group 1, but then I add the 0. Okay? Well, again, B2. 0, 0, 3. These the 0, 3 here are the one that correspond to these entries. The extra one I added because I'm padding with 0 wherever I don't have stuff. Okay? We can keep on going. I'm not going to do it because it's boring. And what I'm trying to say here is that if you're now asking how many ways you can, now we can say, okay, try to write a W as a superposition of so you basically say, I take a small vector, long artificially by padding 0, and I sum. How many ways, now I give you this vector, how many ways you have to decompose it in vectors with entries in the groups? Many, many, many possible ways. You agree? Why is this important? Because this could be that if you have to somewhat build a norm, if you want to describe the norm of this vector out of its components, out of its parts, you have to sweat a bit because there is not a unique way of doing it. Okay? If I give you, say, B1, BG, okay, then there are many ones that are going to give you the same vector. What we want to do is to define. What we're going to do is define a norm which looks complicated. It looks like a legitimate norm and it's somewhat like a minimal norm. And then we try to convince ourselves that it does what we want, which is select groups rather than discard them. Okay? So here, for now, we just appreciated the fact that there is this kind of indetermination in the way you can decompose a vector into its over the different groups. Does that make sense? So I think that's all the notation I need. So here's what we need to do. We basically have to say that to assign to this vector v a norm written in terms of components, I'm going to find all the possible vector b1 and b2 that allows me to build this vector w. Okay, so I start from w and I want to build the norm. So what I do is that I'm going to look for all the possible. This is not an algorithm. This is just the description in Word of a definition that is. So I want to say it in words before writing it down. Okay, so I'm going to define the norm that is corresponding in words to the following operation. Take w, find all the possible way to decompose in vectors. Here I gave you 2. You can imagine that you have a lot more. Among all of them, pick the one that gives you the minimum sum of the norms of vectors. Okay? So in some sense, the most parsimonious way of building this vector, where parsimonious here means take component vector with small norm. Let me write it down. So we are going to call this the group lasso with overlap penalty. And what we want to do is to minimize the sum of the norm of bg. So g goes to 1 to g. Okay? Over what? Over generic vector b1 bg. But then I have to put a condition that says that this vector b1, bg are related to my w. And what is the condition? This one. That if you take and do the lifting of this vector in the right dimension, if you pad them with zeros, they should give you the vector you care about. Does it make sense? Half of you nods and half of you are like. Again, in words, this basically says, many ways to write the same vectors over coefficients. I'm going to assign a norm, which is among all those ways, the one that gives me a series of vectors with minimal norm, sum of the norms. Okay?
So these smaller component vectors, so like data bars of the units, do the elements have to be contiguous, or is it just randomly taking elements?
No, this guy. So I give you a rule. So each bg lives in the. So I start from here because I didn't want to. So whenever you see b1 is of this size, okay, and whenever you see b1 bar, it looks like this.
Yeah.
That's it.
In the definition of, I guess it was better for you to say b1 instead of b1 bar. Like in the diagrams you've drawn, all that are contiguous. But is that
No, doesn't have to. So what he's asking, I understand your question, sorry. So here I'm just putting this guy and those guys. Can I actually do, say, maybe we can even do it here. Can I actually do that? This is group 1, and I don't know, this is group, yes, you can do whatever you want. Okay. No, they don't have to be continuous elements. It can be any groups, okay? Also in the case of non-overlapping groups, that was true. They don't have to be groups like this. They can be in any way. It doesn't really matter. Okay. Okay. Now, yep.
So for the B1 bar and B2 bar, when you're finding the RGLO, would an acceptable
When you're finding what? Sorry.
the minimum with the RGLO?
This guy.
Yes. Would acceptable B1 hats and B2 hats for this example have been 1, 1, 0, and 0, 1, 3? Like, can you split values between different BGs?
Say it again. What do we want to do? So the only rule of the game is that you cannot. So there are zeros that are sacred, which are the one where you put the padding. Okay. So this is the padding, and this is the padding. Okay. This 0 is a 0 that you can touch. These zeros you cannot touch because the rule of the game is that you choose this part of the vector, and then you pad them with 0 so that they give you the right one. So you can do whatever you want here, and we can ask ourselves what is the one combination that provides the best possible writings of the vector 1, 2, 3. But the important bit of this story is that here you cannot put anything but zeros. Does that make sense?
So if we split the 2 value between the 2 vectors. So that
That's essentially the basic idea, kind of a symmetry idea. What we want to do is actually take a step further and seeing actually, we're not going to study in more details this norm. We're actually just going to do a certain manipulation that shows that to some extent you can reduce this to the non-overlapping group up to some manipulation. Okay? So what we want to do now is, you agree that there was a problem in trying to define a norm because we have multiple ways of defining norm, multiple ways of writing the vector. You agree that this seems like one way to write the norm. I hope you also agree that at this point, why this should be a good idea to select rather than discard groups is not completely obvious. Okay? Or if you do have an intuition, you can tell me. I don't have a particular intuition on why this is the case. So that's the thing we want to ask next. Why is this norm? So now I want to use this norm, this here. Okay? And I would like to understand how this is a good idea. Why is this a good idea? Okay? And what does it do? So far, so good? The next thing is kind of a slightly annoying set of notation. It's actually relatively simple. So we're going to write down the problem with that norm. We're going to let the inf come out. So what I mean is, let's write down the problem we want to try to understand. I'm going to rewrite this in a slightly more compact form, which is that I say that this is the sum of the norm BG, G from 1 to capital G, and I minimize over B1, BG. Let me omit the space where they are. They are the vector with the right size, the group they belong to. And then I still have to put the constraint that relates them to this vector here, which is that B1, BG bar sum over G should be equal to W. Okay? So this is the problem we want to solve. Now, what is the idea? We want to see what take this minimum and we shift it in front of everything. Okay? It's just an extra minimization. What is the effect if we, instead of minimizing just over here, we minimize over everything? This is depending on W. This is depending on B1, BG. So I can do this. I can say, okay, this is variable 1, this is variable 2. Let's see what happens. Okay? So the first thing we want to do is basically say, okay, I'm going to do this. Then I have to write, sorry, there is a square here. Okay, so I took this stuff and I put it out. Then what do I want to do next? Well, in some sense, these two minimizations are redundant. Okay, because the moment you minimize over B1, BG, and you include this, you're done. Okay, so what I mean is that we can actually rewrite this as minimum over just B1, BG, where we basically replace this W with this expression. So we're going to write sum x hat, and here I'm going to put BG, G1, G, minus y hat, plus sum BG, G1. Sorry. Okay? So what I did from here to here, and I said, oh, here I minimization over W, then W was written that way. I'm just going to say, okay, W is of that form, and I just minimize the sum, so it's fine. I can just do this. Okay? So far, so good? Now we're going to do some massaging, okay? And let me give you the spoiler what's going to happen. You're going to find out group lasso without overlap in a fake matrix when we replicated by hand the rows that correspond to the variables in the overlaps, okay? That's what's going to happen. So if what I just said doesn't make sense, you're going to see it in a second.
It's a standard expression for lasso, right? Just yeah, because this is like an actual value and this is quite a
It's not. So there are a bunch of different things here, right? So what he's saying is this like the lasso? Well, like the lasso, it's not immediately because this guy is actually a norm rather than a, so this looks like a bit like the group lasso, okay? But when you do group lasso, you don't have this complicated stuff. Instead of optimization, so the closest thing to this guy is what I've written over there, what is still written over there, right? But in what is written over there, the W decomposes exactly into non-overlapping terms, whereas here, I still have overlapping terms. So if you try to solve this, good luck. How do you do this? Try to use whatever I said there. You cannot do it, okay? These things are overlapping. You still have the problem with overlaps. You see, there, when you do W, again, there is always a natural decomposition of W in two parts, and they don't overlap, okay? Because I'm assuming the groups to be non-overlapping. Here, the whole game is that now, unfortunately, we are in this situation where there are multiple ways of writing my W. And so here, my W, this is not just a concatenation of two vectors. It's just an overlap of two vectors. It's more complicated than that. So it's not quite the lasso. It looks more like the group lasso problem, but I still have to deal with this. Because I would like here to put something like B1. Say I have just two variables, just for this reason. This is like B1, B2 is exactly this situation. I have to sum them up. If I could disentangle them and just concatenate them, then it would just boil down to exactly the usual group lasso. What do you have to do? You have to replicate some columns here. So let's see that, okay? So just think what happens. Let's just think 1 second. Let me do it. You have this matrix here that is going to hit this vector here. So it's just a sum. So I can let this sum in, okay? So let's just make the first case. You have x hat, and this x hat is going to hit b bar 1, okay? B bar 1 looks like what? Okay, you're going to have this matrix here. Then you have this vector. But this vector b1 has only some entries different from zeros, right? Say the first half. So when I do this multiplication, and here there are a bunch of zeros, this is equivalent to doing what? To considering just the first half of the columns and multiply just to the vector without the padding of zeros, okay? So it means that this guy is actually equal to x, restricted to the indices that corresponds to group. That's what this notation means. I just take the columns that correspond to the right group, and then I have to apply this to what? Not to B1 bar, but to B1 without the zeros, so it's B1. You agree? Let's do it. Let's keep on going for 2, and then it's done. It's just a notation. I want to be sure that you see it. Suppose that I have to do now x bar x hat B1 plus B2. Okay, I just have 2, now we're going to have G, but we just do it, you see what's happening. So it means that, okay, this guy hits this and you get this, okay? If you now hit the other guy, you get the same thing with G2. So you're going to get x bar G1 B1 plus x bar G2 B2. But this means that now you can take this whole thing and think about, a matrix. Let me call it x tilde, which is what? I take the matrix X. I have to take these columns to build the first part. Then I have to also to take this column, okay, to build the second part. So this is X G1, this is X G2. X tilde is the concatenation of these two matrices. Okay, so I do X tilde, the concatenation of X G1, X G2, and I'm sure I screwed up whether it's column or rows, or maybe not. No, maybe not. Okay? Does it make sense? So what is this matrix? Is the matrix where actually by replicated, whenever there is an overlapping thing, it's going to appear more than once. Because you see here I took the columns that correspond to G1, the one to G2, and they happen to be overlaps, I take them all. What do I have to put here? I have to put a vector which is what? Just the concatenation of B1, B2. Okay? So I'm going to put B tilde. And what is B tilde? B tilde is just, so this is X tilde, and B tilde is just the concatenation of B1 and B2. Okay? That's all. Does it make sense? So we're just going to use this now. Okay? So given that, what you see is that I just have to use this thing we did, but rather than doing it for 2 vectors, I have to do it for G of them. But the rest is the same. So what I'm going to do is that basically I'm going to say, okay, I'm going to minimize over, I guess, still B1, BG, x tilde, B tilde minus y square plus lambda BG, G from 1 to G. Okay? And now it is true, you know, what we wanted is true. It is exactly of that form. Because now I have, when you see B tilde is exactly decomposed in B1, BG. They don't talk to each other. They're just really entries. I'm not in this bad situation. There is a unique way. You give me B1. There is B tilde naturally decomposing only one way this way, and given B1, B2, you can only B1, B tilde, so you're good to go. Okay? You good? So this is actually easy. It's just like, you know, in the notation, and the more complicated, the most annoying part is just this, but it's relatively easy. Notice that in this simple calculation, we actually achieve 2 things. One is that we have an algorithm to compute things. Okay? We can use this. You want to solve that problem, and you have the code to solve this problem, but you actually want to solve this problem. All you're going to do is you're going to take the matrix X, okay, generate a new matrix X tilde where you artificially increase the number of columns, and then you're going to just plug it in there. You agree? Then you can make 2 comments. First of all, I claim that this shows why this guy is selecting groups. It doesn't break groups anymore like that guy, you know. So you can use this, when I say algorithm, in this computational procedure, right? But if we were to use this penalty on those overlapping groups, we said we're going to just discard groups. I claim that once you use this, you can read out of this way of computationally find the solution. You're going to select groups. And why is that? Well, because you're actually going to discard groups, but you already saved groups. You know, you by artificially unoverlapping them, okay? You do whatever you want to group 2 because I already saved of group 1, okay? So I'm going to select them. And if they're important, I'm going to take them up. Okay? So this is the one, this not only gives us an algorithm, but also gives a way to understand the big difference between this norm and that norm in the case where groups are overlapping. If you just use that norm, you kill groups and you're left with complements. If you use norm, you're actually, because it's equivalent to doing this kind of computation, this gives you an insight on the fact that you're actually preserving groups, okay? Because essentially you copy the overlapped variables. Along the way, also, this is a good way to compute a solution, okay? I'm not saying it's a good, actually. It's a way to compute a solution. Is it a good way? Well, first of all, okay, the difference between this and this, here you break groups, here you preserve them, and because of this is one way to convince yourself that's true. Any questions?
Should combine only the columns where still has zeros in it, right? So how are we going to define that prior like, without learning data?
No, wait, there are zeros and zeros in these games, right? So again, there is the zero padding, okay? So I mean, it's fairly easy. A procedure. Suppose this case, okay? In this case, I know that group 1, okay, is coefficients 1 and 2, and so entries 1, 2, and group 2 is 2, 3, okay? You give me X. I'm going to build X tilde. How? Well, I'm going to take the columns, and then I'm going to add, so I'm going to add column 1 and 2, and then I'm going to concatenate with column 2 and 3, okay? I don't have to solve anything beforehand. You just told me the groups. You told me the indices of the groups are these guys, and I just repeat them, okay? That's it.
So we need to know
The groups. In this game, everything we've done so far, you need always to know the groups. And it's just a matter of whether they're overlapping or not. If you know them, you keep on going. So you need to know the groups, absolutely. Okay? Yep.
So take this simple example over here where you had 3 components and you split it up into 1, 2, 0, and 0, 0, 3. And then you split that 2 halfway between the two. So then it's 1, 1, 0, and 0, 1, 3. Okay. If you ran this algorithm and then it selected only one of those groups, it would like put half of that 2 on that first group.
Yeah.
Right. Whereas if you had done the original algorithm with non-overlapping groups and just done 1, 2, 3, and also selected the first group, then the whole 2 would be.
No, but just to so say if you do this guy, so if you select this, if you use the first method, you're only going to get 1 entry. Okay, you just get 1 entry different from 0. In this game, you're going to get 1 entry different from 0. You see, I have overlapped, and I'm going to use this penalty.
No, I meant the one with non-overlap. I'm just asking, like, what's the significance when you split an element between different groups and then one of those groups gets chopped off versus if you had done non-overlapping in the first place and the same group got chopped off, so you kept.
I don't understand.
Yeah, it's kind of a convoluted question.
No, but I guess because the question is so. The structure of the groups is a prior. You don't choose it. It's not for you to say, I choose this or that. Okay, we can take that point of view, but that's not what we're doing. We're saying the group, the prior we have is that there are groups, and we want to deal with them. Okay, and in the case where we have no overlapping groups, it's a no-brainer. When there is overlap, we have to decide what to do. And all I wanted to show here is that you have two basic choices. One is recycle what you've been doing, in which case in this case you're just going to get 1 entry at most different from 0, and you're going to break a group. Or you can go this way, in which you're going to select the group and keep it. That's it. So does that make sense? I mean, beyond that, if there is, I'm just a recording effect that there are these, when there are overlap, there are at least these 2 different situations. Okay, that's all. You had a question?
Yes. So if you have a lot of overlap between these groups, doesn't this get really expensive?
Absolutely, yes.
Calculating that? Okay.
Absolutely, yes. That's why I have a paper. No, yeah, that's actually true. That's exactly what motivates looking at alternative way of doing it, and indeed I have a paper on this. And basically the idea is, okay, that's cute, it gives some insight. The reason why I do this is not to suggest that this is the killer way to do this. It's, what he's commenting is, if you have a ton of overlap between the groups, you're going to get a matrix that kills you. Of course, time-wise, wouldn't be too bad, but memory-wise, this might be a disaster. And even time-wise, you're artificially augmenting the problem. One thing one can ask is, okay, but we know what is a proximal operator. You remember that the proximal operator was just, let me just remind you what it was this, the proximity operator was this thing that, given a functional and v, what you're going to do is that you're going to do the minimum, so the argmin over u of u minus v squared plus ru. Okay, so it's kind of, the proximity operator is kind of an optimization problem itself that is some kind of regularized minimization of the penalty. Okay, so one thing you can ask is, can I compute this for this penalty directly? Here I kind of get a convoluted way to get one way to avoid asking this question, but you can ask the question. If you take this penalty, can you solve this? And does it have a decent form? Yes, in the sense that indeed it becomes a quite nice problem. You see that there are basically some projection over certain cylinders that are the one defined by these norms. So it has some nice form. You can use alternating minimization procedure. You have convergence guarantees. The bad news, if you want, is that it doesn't have a closed form solution. You really have to solve an optimization problem. So what you're going to do is that you're going to have an inner iteration and an outer iteration. This is the outer iteration, something that looks like that. But then the computation of the proxy itself is going to require an inner iteration. And this has motivated a bunch of theory, if you want, that some of it was known, some of it was not. Where basically you ask, okay, what is the price? A natural question from an optimization point of view is, can you ensure that error don't adds up in a bad way? Okay, because you see, every time you compute a prox, you're going to do it up to a certain precision, which means that the overall precision of this is going to be affected by this, and you want to be sure that you can show that how many iterations you have to be inside or outside to be sure to have a final accuracy. Okay, and so people study this kind of stuff, and they also study when they say, "Oh, I'm going to accelerate this. Can I also accelerate the one inside? What is the total gain, and so on and so forth." Okay. So I'm not gonna show you because it's kind of long, But indeed, you can perform this optimization in the case of this norm, and you come out with a certain structure problem. Okay. Memory-wise, you'll be fine. You pay a price in a bit more in time because now you have to do inner iterations to solve this question. Okay, but that's a good point. Other questions or comments?
I think I got most of it, but I'm confused about the simple example 1, 2, 3. You try to split it into two. For B1 is 1 and 2, and B2 should be 2 and 3, right? Why is it 0 and 3?
Say it again.
I think I got most of it except the B1 and B2 part when you're splitting on the simple case. You're splitting into 1 and 2, and then the second one should be 2 and 3, right? Because you're duplicating it. Why?
Give you a precise definition here. This is just kind of. So, what are you asking? What did I do at the beginning, or how does this fit there?
I'm just saying, why is it not 2 and 3? Why is it 0 and 3?
Because the rule of the game, so this is sloppy, okay? What the precise version of this is that given a short vector, I'm going to make it artificially long by padding with 0. And the fact that I obtain the same vector, it means that when I sum them up, I obtain the vector I started with. Suppose that I pick this guy, which is the one you want. When I do the padding version, I'm going to get this. When I sum these two guys, I'm going to get 1, 4, 3. And this is not the one I want at the beginning, which was 1, 2, 3. I violate the fact that I want my vector to give me the first vector. Does that make sense? Yeah.
Quick question of whether or not you get to split the penalty. My first if W, you get to split the penalty between the groups, or the full coefficient should be penalized.
I don't understand.
Like, I think what he's saying is you have a 2 in the second spot. Should its magnitude get penalized by both group 1 and group 2, or should you only count it in one group?
Again, so the way I try to answer this question is by showing you that equivalence. Where the way you can think about it is that you actually duplicate. Study the geometry and the specific form of this norm is a bit more complicated. Okay, but that thing tells you that when you use it, is equivalent to basically saying duplicate it, and then one time you take the 2 and you completely penalize it. One time you take the 2 and you don't penalize it at all. This is the way I try to answer this question. Another way would be to basically understand a bit better the nature of this norm without going that way, which is possible, and you can do it. But I don't have an easy way. There might be one, but I don't have an easy way to explain it. So my answer to this is just I'm going to replicate it, and one time I kill it, and one time I leave it be. Doesn't sound great, but this at least tells me that it's doing what it's supposed to. Yeah.
This is a bit of a high-level question on sparsity, but it feels like the most intuitive way to do this would be to add a constraint to the optimization problem that enforces a maximum on the L0 norm just as a constraint in the overall optimization problem, and then solve an optimization problem. Other than computational reasons, is there any other reason why we wouldn't do that?
You mean a minimum norm? You want the sparsest vector, you mean?
I mean maximum, say that
the zero norm is counting the number of non-zero elements. So if you make the maximum, you're looking for the worst possible sparsity. So I guess.
Sorry, I'm like set a hard cap.
Okay.
The L0 norm is less
more than something. Yes.
Sorry.
See, but this is just going back to two classes ago. Why don't you do L0 norm to begin with? That's the question.
Yeah, is it just the computational?
Yes. Yeah. When it says NP hard, that's an annoying part of that statement.
So if the optimization could do it, that would be.
It cannot. It cannot. This is one way to do the computation. It's basically saying, it's provably hard in the general case. So you try to show that there are cases where you might not be able to do L0 itself, but at least you can do a proxy, which gives you the same solution as if you were doing L0. So it's absolutely computational, and this is absolutely what we've been doing. Okay. Now we're just making it fancier. Okay. And then, yep.
Is the derivation for the kernel case straightforward, or like?
You have to wait 2 minutes. it's somewhat annoying from a notational point of view. So I'm going to try to simplify as much as I can because it's completely trivial in a way. Okay. In fact, we have to first ask a question in the linear case, just this, and do something we've been doing for many times, to get the representer theorem, and then it's done. And then we can just stop and appreciate what we did. That becomes pretty trivial. Okay. So I'm basically going to ask you first to do something relatively simple and then to have a bit of imagination, okay? I tell you the direction. So he asked me, what about if I want to go in the direction of kernels? And if I remember from the beginning, I said L1 and kernels don't like each other, okay? It's a fact. You know, L1 is a notion where you have to condition over a basis. The basis has to be finite, otherwise good luck making any kind of computation. Kernel really something where you use the RKHS norm. There is a kernel hiding somewhere. It's the span of the basis. It's the linear kernel, but you've not been using it at all, okay? So it's there, but it's not so important. So in some sense, the question is, can you let kernels entering a bit better into the picture in a bit more substantial way? Kernels were useful because it allows to go from parametric to non-parametric. So it would be nice to go a bit in the direction of non-parametrics, which is not obvious at all here. Okay? Because if you just say, oh, I'm going to take the number of variables and let it go to infinity, and then what? What do? You take infinite matrices? That's kind of annoying. Okay? So what we want to do is actually go in the following direction. It's going to take us a while, so this is again a spoiler. We're going to, instead of talking about groups, we want to talk about kernels. And basically we want to go in the direction where rather than one kernels, we allow ourselves to use many kernels. Okay, and possibly saying that we don't need infinitely, so we're never going to look at infinitely many kernels. We're going to look at many, but always finite. But rather than many finite dimensional groups, we're going to essentially look at infinite dimensional groups. This one is going to be a kernel, and the feature map is going to be a natural way to go from whatever is here to kernels. Okay, so we go in that direction, and then we're going to basically what we want to do next in the next 10 minutes is to do that, and then hopefully if it doesn't take more than 10 minutes, we can just look at it and understand why would you want to use more than one kernel. So we're going to go this way, okay, somewhat bottom up. So the first thing we want to ask has nothing to do with kernels, so leave them away, okay? And all we want to ask if we can find some kind of representer theorem. We knew that there was no interesting representer theorem for L1, essentially because the structure of the theorem was broken. The fact that you have the norm split nicely, it's gone. You know, if you look at the proof of the representer theorem we gave, the very first one about the minimizer, it's gone, it doesn't work anymore. So still here, we're going to have some kind of representer theorem. Let me tell you how. It's not going to be at the level of the W, the big one. It's going to be at the level of the W in each group, okay? And to do this whole discussion, I'm going to restrict myself to the case of non-overlapping groups, which means that I'm going to consider at some point reproducing kernel-based space that don't have intersection, which is a super strong assumption. But you can extend it, it's just annoying. So bear with me, and we're just going to do the following. We're going to go back to the basic case. Okay, so I think I can delete anything here. I'm going to keep it around for a bit more. So I'm happy with this. So we start from this board, and we want to work on this guy, okay? Not on anything else. So the first observation is the following. It's very simple, okay? How much is f of x in our model? Well, it's wx, okay? But now I also have a notation. I'm in a non-overlapping case, so we make sense of the notation with the parentheses and the number. I'm just going to do a case of two non-overlapping groups, again, just for the sake of simplicity, at least at the beginning. So how can I write this? I can write it as W1. So W is just W1, W2, and similar is X is X1, X2. So I can write this down as W1, X1, plus W2 x2. Okay? These are not the same inner products. These are vectors of different size. I'm just going to skip it again, not to burden the notation. Notice that at this point, nothing prevents you to think that the situation we're dealing with is the one we just have two different set of features. Okay? So these numbers happen to be numbers related to the presence of corner in an image, whereas these numbers were related to the presence of color in an image, okay, or something like that. And I just concatenate this information. I'm going to use it. Okay? This is not an example that I made before, but I could have. Okay? This is the case where I actually don't have overlap. All right? So in this view, it's quite natural to call this guy f1x and that guy f2x. Okay? So if this start to go in the direction, we're going to have a function which is a sum of functions. In this case, it's just a stupid notation, but we're going to make it more general because at some point we're going to replace this x with a feature map and this x1, x2 with feature maps. For now, this is just a notation. Now I'd like to just convince the proof, but just to give you a feeling, because I may be actually going to do the proof in the P set. So I want to convince you that you're going to do the proof in the P set, that you're going to have a representative theorem for each of the W1, W2 separately. Okay? And so again, what was the representer? If you remember in the linear case, just to suppose you're doing ridge regression, linear kernel, and blah blah. What does it mean to do a representer theorem? Well, you can write it in two ways. You can write it, say, F1 is in the linear case, okay? It's just a superposition of kernels. I need some space, so I'm going to cheat this. So this was the representative theorem for SVM-like stuff, okay? Here I want to do the same. The direction I want to go in to prove something like that, but not for the F, for F1, F2, F3, and so on, which makes sense because you see at some point I'm going to use the norm of those guys, the L2 norm of those guys. So what we want to prove is something that looks like this. It's like W1, okay? And then I have to put 1 everywhere I should put 1, which is here, here, and here. So what does it mean? Here I take the vectors, but not all the vector. I just need in the training set, I only take the entries that correspond to the first group. Okay, this is group 1. And these are the entries of any point just on group 1 and keep on going. What is it? It's just n coefficients. You just give it I1 because it corresponds to the 1. Okay? Let's write down this. Okay, let me just rewrite this. Okay, when you write x hat w minus y hat square, this is going to be, again, I omit the 1 over n. It's going to be yi minus, this is wxi. But in this case, it's just w1 x1 plus w2 x2 plus lambda. And then I have what? Norms. I just have 2 in this simple case. So I have lambda, and then I have sum w1 plus w2. Okay? I just rewrote, if I didn't make too many mistakes, which I'm just missing at least one parenthesis here. These are 2's. I just rewrote this group lasso functional just in the case of 2 groups, okay? Because I want to take a look that if you remember the way we proved the representer theorem, do you remember how was the proof? We basically we said, okay, I want to show that F1 has this form, okay? And one way to see is that this is equivalent to the fact that W1 has to be on a certain form. How? It's not a generic vector of size group 1, but is These two things were equivalent. We used them a bunch of times, okay? And I'm going to skip the proof because you basically is the one who has to do it, but you can kind of see that the exact same proof that we did for ridge regression is going to work. What was that proof? Basically called this function the nice ones, okay? And then we checked that if W1 has some other stuff, it doesn't matter because there is this inner product that kills it. In some sense, you do an orthogonal decomposition, and then you have this norm, and the best thing is to kill the part of the function that we don't like. And we're going to do it twice here. Or actually, you're going to do it twice here. But there's really not, it is really kind of the same, okay? So this says that at the level of, so if you believe this, which again, I just sketched this to just give you a feeling of how the main ingredients we saw for ridge regression are going to be there. If you believe that, it means that at the level of groups, we're going to have a representer theorem. Each group, okay, we can do a representer theorem. And indeed, it turns out that you can sweat a little more, and you can design a proximal operator that works on the coefficients C rather than the coefficients, the one over there, okay, on the W's. So proving this, which is what you want to do, is elementary. You don't need anything. You don't need any advanced tools. To derive the proximity, to derive an equivalent expression like this for the case where you're dealing with the C's, that takes a little more work. Okay, it does take a little more work. It's similar to the proof by induction that we did for logistic regression, SVM, iterative regularization. There is one extra couple of complications related to the fact that you have a prox operator there. So in some sense, you have to check how the prox interact with the transpose. But you know, I think I put it in the notes, and you can look for details. But let me give you the expression. So I'm telling you, okay, for all this W, I have a representer theorem, and now rather than computing W, I compute the C, because then I'm done, and I can just use the C in this expression. Okay? How do you compute the C's? Well, you just do a prox operation that looks like this. So you're going to have So I have to explain what I wrote, because what is CT? Okay, CT is actually the concatenation of all the C1, C3, C4. So in our case, we only have two. So this is going to be C1, C2. Okay? So I told you that I'm going to associate to each W as a vector C. This is the first one. Sorry, this is CT. So this is the one for the first, and this one for the second. And so every time you see a CT, means there is a vector, there is concatenation of two vectors of size n. So the total size of this is 2n. Okay? What is K hat? K hat is the matrix, which is concatenation of two kernel matrices, or if you want, gram matrices. Again, this is just, there are no kernels for now. These are just inner product matrices, okay? And what is this? This is like, I take my data matrix, I keep only the component to the first group, and then I do it in times itself. So I'm just going to write one of them. So this is K hat 1 is what? What we call X hat restricted to G1. This is the group 1. And then we're going to take the inner product of this guy against itself. Okay? So they're not kernels right now, just inner product. It's only that I'm killing the first few variables for one guy and then the other variable for the other guy. Okay? Again, how you derive this is not super straightforward, okay? You know, how you go from, you know, the problem to this guy. Once you have the representative, you go here. It does require a couple of lines. But the reason is that you can check is that this is actually relatively, again, relatively easy. You have to pay the price that you're dealing with these many kernel matrices, so it's pretty big. Okay, this is n times g. Okay, so this stuff is n times g, so it's big. And similar, this is of size ng, is a long vector. I still also have to tell you how to compute this prox, okay? Because if you look at this prox was actually doing thresholding on the W's, okay? Whereas here, I only want to deal with C. I have it in the back of my mind that I want to make W big, okay? So what you're going to do is that it turns out that the prox when acting on CT, or any C, for what matters, so let me say CT so that you remember this is a long vector, is again going to be a block operator, is the prox on C1 and the prox on C2. Okay, so it's again a block operation. I'm going to act first on this guy and then on that guy. And what does he do? You just do the same thresholding as before. You just have to be smart about noticing that you can compute the norm. So if prox alpha C1 J is going to be equal to 0 if, say, norm W is as before, is smaller than equal than alpha, and otherwise it's going to be equal to C1J minus alpha C1J divided by norm of W1. Okay, so I'm almost done. I just have to say one more thing, but because the notation is slightly annoying, let's parse it. Okay, so for now we are just rewriting the group lasso with the out overlap. Okay, and we are saying it is just noticing this expression. It is possible to prove a representer theorem. Once you have that in mind, you can try to algorithm to compute the coefficients in the representer theorem. And it turns out, and we're skipping the proof, that this is the kind of iteration you have to do. The argument only has inner product matrices of the groups defined by each group and the data, and this longer vector, which is the concatenation of the representer for each group. And then the proximity operator has, again, a block structure. And the block is written like this. It's basically setting to equal the C, okay, the vector C. Notice that if you set to 0 all the vector C, you're going to get 0, okay? Because if I take a function and I put E to 0, I'm still going to get a 0, okay? What is the only bit that I'm missing that you still have to complain and I have to tell you? Suppose I have to run this. The rule of the game is that W should not enter the picture, right? Because if it does, we won't be able to kill W at once. But remember, we know that holds, that the W's we're looking at are not generic W's, are the W's that have that specific form. Which means that if I give you this, how much is norm W square? Well, it's just ij1n xi1 xj1 ci cj. Or in other words, if you give me the notation written here, it's going to be equal to C, C1, sorry, C1, C1ij, and here it will be C1 k hat 1 C1, okay? So it's the quadratic given by the inner product of those specific variables, okay? Again, it's a bit overloaded, unfortunately, but there's really nothing interesting going on. We're just manipulating things. We're actually doing stuff that we've been doing like a couple of weeks ago. That's it. Now, whenever you see that symbol, whenever you see this symbol, you should think about that, and that's it. I give you a procedure that is completely independent on W. You only use the data, the C's, and it runs. And then at this point, you sit and you shout, kernels! Because basically what I'm saying is, well, let's stop 1 second here. Is there question about this before? Because right now we finished to do the calculation. All we're going to do now is change notation, Okay, we're just going to say, I call it x1, I'm going to call it phi1x. You see this stuff here, it's just going to be a kernel matrix for real. This symbol is really going to be a kernel matrix, and that's it. We don't have to do anything else. We just look at it and it's like, all right, fine, okay, you can do it, okay?
Explain the reason why the denominator is W here instead of like C, for example. Like why do we divide by the norm of W?
Well, it turns out to be the right thing if you want, and if you want, it's just because you still try to keep groups, right? So this is still a natural quantity to kill the group, okay?
So if you put C there, then if you regularize the norm of C, you will still regularize the norm of W, right?
In a different way, though.
So it seems like
So so what I'm trying to do now is not to invent a new regularization, just showing that the regularization I already gave you can also be written, solved in a different way, okay? So I'm not saying, the rule of the game is keep this because I say so, and just try to find a different way to compute the solution. Nothing prevents, and you can do, is to say, I'm going to start with assuming that W can be written in terms of C, and then I put here a norm on the C's. You can do that. It's just a different algorithm. They're not equivalent. Okay? This is one possible way to answer. Even if I give you this solution, even if I give you this, here I'm still keeping this. You can say, well, but you gave me that. Why don't you put this thing here? Because I don't. It's another algorithm. Okay? And we can discuss the pros and cons, but that's just another choice. Okay? It's the same thing when you do kernel method and you do the representer theorem. Why don't you just kill this k? It's another thing. It's another method. Okay? It can be seen and can be related. It's what is sometimes called coefficient regularization. It can be related to ridge regression. We have not done it because it doesn't really add a lot. Okay? Same thing here. So here we want to stick to this because we're going to give an interpretation of this norm just in 1 second because that's going to be extremely easy. Does this make sense? So you can do it. You just get another algorithm, which is not this guy. Any other comments before in 2 minutes we do this? All right, so let me tell you. The whole game here, so we're going to finish next class, okay? But I just need 10 minutes. And now I just want to show you, not to let it hanging completely. So the game is that we're going to replace x1 with phi1, okay? Say phi1x, which is going to be any feature map in the sense of kernels. And whenever you see k1, okay, or rather k hat 1, this is going to be just a matrix with entry ij given by phi xi1, phi xj1. Okay? That's it. So whenever you see, and we're going to assume that we're in this nice case where all these spaces don't overlap and the feature map is 1-to-1, so that whenever you see something like this, this is actually going to be equal to the norm of a certain function in a reproducing kernel Hilbert space given by the kernel K1, which is just this guy here. Okay? That's it. So we basically have to go there and just do a bunch of change of notations. Okay? And when we say that our W is a sum of these point, we can also use this notation because, say, when I say that my W is sum of this guy, okay, the extended version of blah, 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 this will be replaced by the fact that my function is a sum of function G that live in different kernel Hilbert spaces. So the FG are going to be in a reproducing kernel Hilbert space with kernel KG. So go home and stare at that for like 20 seconds, because all we have to do is now, you know how to solve it, you know how it looks like. All we have to ask is, why would you do this? Why is this situation? We can give a couple of examples, and they're pretty different between each other. It will be the case where, for example, you do combination of kernels because you want to do data fusion. You have a kernels for colors, a kernel for text. Okay, a kernel for image, a kernel for text. You want to mix them up. Boom, you can do it for this reason. Then you're saying, I have polynomial kernel and Gaussian kernel. I want to boom, you can do it for that reason. Or perhaps the more interesting case is, I want to do variable selection in a nonlinear way. And then that's kind of a more interesting. We're going to put one nonlinear kernel per variable. So each of those fg are going to depend on just one variable. And again, we will not have to do anything else but thinking about this because we sweat everything here. Okay, so all we have to do is to look at the symbol and use some imagination. Say, oh, it might mean that too. Oh, it might mean that too, because the rest is fine. Okay. All right. So I'm over.